My name is Edward Morley, and the project I'm going to be talking about relates to measuring the speed of light and proving the theory of luminiferous ether. Ether is a theoretical medium that we thought electromagnetic waves used when being transmitted, much like sound waves are transmitted through a medium such as air. In our experiment, we were trying to find the speed of the Earth through the ether. One thing we knew was that the Earth's velocity around the Sun is about 30 kilometers per second. If the speed of light was constant in ether, we could compare the speed of light in the direction of the Earth's motion and at right angles to the Earth's motion. This would allow us to figure out the speed of the Earth, because it would basically create a wind as it moves around the Sun, just as your automobile would create a wind as it drives down the street. The experiment took place in Cleveland, Ohio, at the Case School of Applied Science. There's a restaurant there now named after us. Just as good as a Nobel, right? Other events going on at the time of our experiment? Let me see. Herman Hollerith received a patent for his punched card calculator. And then Dor Eugene Felt received a patent for his comptometer. Gottlieb Daimler released his first automobile that year. Thomas Edison patented the kinetoscope. Oh, and we had our first Groundhog Day that year. Albert Michelson was the head of the project. Brilliant man. When he was only 25, he made an outstanding measurement of the speed of light. He then went on to create the interferometer. Naturally, I was elated that he asked me to collaborate with him in this experiment. What was my role in the project? Well, the first thing Michelson and I worked on was a new and improved interferometer. This time it would have multiple mirrors, and the path length would be about 10 times longer. So basically, you have a light source, and the light is directed at what's called a half-transparent mirror, which is just as it sounds. Half of the light bounces off, while the other half goes through it. The path is split into two, and the paths are directed toward other mirrors, where they are reflected back into the original half-transparent mirror in the middle. So when these two light paths go back into the middle mirror, they get split up again, some getting reflected and some going through. This allows us to detect the velocities of the light. The theory was that since the light paths were all reflected in different directions, they should all have different velocities through the ether, because the light waves would have decreasing velocities as it flows through the ether. So, we adjusted our interferometer to see any kind of interference patterns in the light waves. But regardless of how we adjusted the interferometer, we observed no change in the interference patterns, which implies either ether does not have any effect on light, or it does not exist at all. Alas, the experiment did not quite go as Michelson and I thought. The idea was that the interferometer would create a fringe shift of around 0.4, but instead it was something like 0.005. So not quite what we were looking for, unfortunately. There were still many believers of ether, but our experiment was sure to debunk most theories of ether. And that's okay. Michelson went on to win a Nobel, which is fantastic. Einstein later went on to publish his work on the special theory of relativity, which states that light is a universal constant. And all that means is that it's something in nature that doesn't depend on any experimental conditions, like sound would, for example. At first, I was very skeptical of the results from my experiment, because I, along with many other scientists, believed fully in the existence of ether. I conducted more experiments with Dayton Miller for a few years. I tried larger interferometers, and I even tried conducting an experiment on top of a mountain. But the conclusions were the same.